My name is Melissa Micah. I'm with the Hydrologic Engineering Center, and this is a lecture on regional precipitation frequency analysis. This video is part 1, Introduction to Regional Frequency Analysis. In this video, we're going to introduce the concepts of regionalization. So what does it mean to regionalize? Suppose you would like to predict the thickness of a pizza crust for any pizza restaurant that you haven't been to before. You might start by walking into your local pizza restaurant, ordering a slice, and measuring the crust. But this doesn't give you a lot of data if you wanted to extrapolate to other restaurants. You could also try randomly surveying pizza joints all across the US, but as we can see in the figure to the left, there's a lot of different styles of pizza that have different thickness of crust. And so if you took all of that data that you collected, this doesn't really help you predict the pizza crust thickness of a restaurant. Now you try measuring pizza crust for only Detroit-style pizza joints. This is getting somewhere. Now you've successfully collected data from a bunch of different restaurants, but you've ensured that the data probably comes from the same population. In this hypothetical, each pizza restaurant is like a precipitation gauge. If we only have information from a single gauge, it's really hard to make predictions and extrapolate. Collecting data from multiple gauges essentially allows us to increase our sample size so long as we assume that they come from the same population. So expanding on that idea, regionalization is about analyzing random samples of the same phenomenon that occur over a region. A region can be defined as a relevant study area, or by the extent of an area that can be considered meteorologically homogeneous. The assumption that we make in regional frequency analysis is that the samples of our meteorological phenomenon have the same distribution, except for two key differences. First, the parameters at any site are affected by sample error, and second, there is a systematic local variation that we can explain. Here's a map of heavy rainfall that occurred in June 2012. The areas in blue received the most rain, and the areas in red and orange received the least rain. Keep an eye on these three locations. The red dot is in Duluth, the purple dot is in Ironwood, and the gray dot is located along Interstate 35 in Minnesota. Notice that the spatial pattern of the storm is highly variable, with some areas receiving a lot of rain immediately adjacent to areas that didn't receive very much rain at all. Here's a similar map for an event that occurred in July 2016. Again, with areas in purple and blue having the most rain, and areas in red and orange having the least rain. The patterns of these storms look very similar, but the storm center occurred in a different location. This storm occurred further to the south and was centered over at Ironwood. If you were to perform a frequency analysis for 3 sites, Duluth, Ironwood, and somewhere in between, you would find differing results. You would find that the 2012 event heavily impacted the Duluth frequency, and the 2016 event heavily impacts the Ironwood frequency. But a site in between would likely predict higher rainfall depths, because it experienced 2 large storm events during the same period as the other 2 gauges. The key takeaway here is that these 2 storm events were very similar, but they occurred at different locations. This storm event shown here easily could have occurred further to the north and hit Duluth. By regionalizing information, we capture the spatial variability that these storms might produce. Looking at multiple gauges tells us more information overall than looking at just a single gauge. In the figure to the right, there's a precipitation gauge with approximately 100 years of data, plotted on a probability plot. If you were to make predictions about the 1 in 10,000 year event, we would have to extrapolate the curve. But there's a lot of different ways you could extrapolate. Our motivations for performing regional frequency analysis is to help increase the sample size that we use for building our probability models. This helps us reduce sample error and increases our confidence in our models. We can also use regional models to help us make frequency estimates in areas where we don't have any information, no gauges, no observations. The limitations that we have to overcome in a regional frequency analysis is that observed records at individual sites can be fairly short. The sites where we do have observations could be fairly sparse in space. This happens often in areas where there's a low population density or in highly variable climatic regions like high elevations or deserts. Now let's talk a little bit about what things we can regionalize. In the context of hydrology, imagine you have two watersheds adjacent to each other. One is very low elevation and has a lot of vegetation, and the other one is very high elevation with steep cliffs. Imagine you have a storm that falls over the first watershed and produces runoff. Now imagine sometime later, a storm with very similar characteristics and magnitude falls over the second watershed and also produces runoff. Do you think the runoff response is going to be similar between these two or very different? Even though the storm characteristics might be similar, the runoff response is going to be very different because of watershed size, basin characteristics, slope, and other factors like that. So when we take observations of weather, it represents a sample at a single location where the station is located, whereas streamflow measurements represent the entire watershed above the gauge, and this can be affected by hydrologic processes, meteorology, drainage area, and other factors. This makes it harder to regionalize something like streamflow as opposed to precipitation or wind speed. Generally, this is why when we regionalize streamflow, we typically only regionalize the skew coefficient, like the map to the right, which shows Bulletin 17B skew estimates. The tool that we use to regionalize is called trading space for time. The idea here is that we have gauges that have a limited period of record. Since we can't extend those records in time, the other option is to expand it in space by collecting additional gauges and pooling them together. The figure on the right shows maximum precipitation for calendar year 1995 in the eastern US. Each dot represents a gauge observation for that year. The size of the dot represents the magnitude of the event, and the color represents the month in which it occurred. If you focus on this area here with these pink dots, these represent a single tropical storm remnant that occurred in September. But could this event have happened somewhere else, like here or here? The key with regionalization is to increase our sample size by pooling together data from multiple gauges. But we also have to make sure that that data is meaningful, that is, that it all comes from the same phenomenon. When we develop regions, we group together observations that are likely similar due to physical causes. The image on the left shows various precipitation gauges located in the Pacific Northwest. Sites located on the south are probably more similar to each other than sites located to the north, and sites that are located near each other generally get a random sample of the overall meteorology for the area. Once we've grouped sites together, we can test their similarity through a statistical lens. So the idea here is that we create the regions physically and check them statistically. And we are usually most interested in extremes, like annual maxima and peaks over threshold. You may recall these steps from the earlier parametric modeling lecture or other lectures in this class. I want to highlight that regional frequency analysis follows a similar process. We take our dataset, select and fit a probability distribution, and estimate quantiles from it. The biggest difference in regional frequency analysis is the first step. Rather than develop a representative dataset from a single gauge, there is a much more complex process to pool together data from multiple gauges into regions. In summary, regionalization is where we trade space for time by increasing our sample size by pooling together information from multiple gauges instead of using a single gauge. This is important in hydrology because our gauges typically have short records of 100 years or less, which is difficult to extrapolate to extreme events. Precipitation and other meteorological factors like wind speed are easier to regionalize than streamflow. And the most important step is to ensure the data are reasonably homogeneous, meaning they come from the same population, as these are the foundational assumptions in regional frequency analysis. This concludes part 1. Please continue on to part 2.